Greetings to all attendees of PacificVis 2020. We are pleased to present our paper towards rigorously designed preference visualizations for group decision-making. My name is Emily Hindalong, and I will be joined by my co-author, Jordan Johnson, in presenting our work. We begin with some background on group decision-making, GDM for short, our concerns with current visualization support for preference inspection, and a brief overview of our work. Group decision scenarios occur whenever multiple individuals must collectively choose from among a set of alternatives. They are ubiquitous in society in groups ranging from families to international corporations and governments. GDM is often non-trivial as the alternatives being considered may vary in subtle or complex ways. As the number of stakeholders increases, so does the likelihood of disagreements that could hamper progress toward consensus. Furthermore, decision-makers may not fully understand their own preferences, let alone those of other stakeholders. Organizations may elect to remain with the status quo in order to avoid addressing these complexities, stifling positive change. One approach that is grounded in literature is to explicitly model and compare stakeholder preferences. This allows stakeholders to not only understand different points of view, but also reflect on their own preferences. Ideally, stakeholders should be able to update their own preferences based on this reflection, resulting in an iterative process of preference elicitation and inspection. Success in this endeavor depends on being able to quickly and effectively gain insights from elicited preferences. Visualizations are better suited to this task than text-based formats such as spreadsheets, because they leverage the pattern recognition and pre-attentive capacities of the human visual system. However, not all visualizations are equally effective, and a poorly chosen graphic can hamper the process of preference inspection. While existing preference visualization designs can be effective for some tasks related to preference inspection, none are grounded in a comprehensive understanding of the needs of decision makers in GDM scenarios. Further, we were unable to find any rigorously developed guidelines for developers of such visualizations. GDM scenarios can vary widely in complexity and scope, from a relatively simple decision, such as buying a gift for a colleague, to choosing a strategy to respond to a nuclear crisis. These decisions may vary in the number of available alternatives or the number of stakeholders. Further, the stakeholders may not be equally important to the decision. The preference models can also vary significantly. For relatively simple decisions, it may be sufficient to simply score or rank each alternative directly. For more complex decisions, such as choosing the best paper at a conference, it may be preferable to consider the alternatives in terms of attributes, such as the novelty or potential impact of the work. Attributes may be subjective, such as a paper's writing style, or objective, such as whether an evaluation was performed in the paper. For objective attributes, the stakeholders provide preferences over the outcomes of the objective assessment. Finally, the attributes may be weighted differently. Given the complexity of the GDM scenario space, as a starting point, we focus on the simplest preference models, where evaluators score alternatives directly. Here we provide an overview of our work, which is guided by the nested model of visualization design. We note that the nested model is usually applied to problems in a specific domain. However, we are examining GDM in general due to underlying commonalities in GDM scenarios across domains. At the domain situation level, we examined 7 GDM scenarios from different domains and identified the decision maker's goals, as well as a number of domain-independent situational features that allowed us to categorize the scenarios. At the abstraction level, we created a data model for GDM scenarios based on multidimensional tables, which are a common abstraction in visualization. We then identified a number of domain-independent goals for GDM scenarios, as well as the visualization tasks that support these goals. We then found we could represent those high-level tasks as sequences of more fundamental visualization tasks. At the encodings interactions level of the nested model, having identified domain-independent task models for GDM scenarios, We then evaluated the fitness of core visualization idioms for the most fundamental visualization tasks. We then used the results of that evaluation to create preliminary design guidelines for developers of preference inspection support tools for the simplest preference models. At the algorithm level, we implemented a prototype tool based on these guidelines that allowed decision makers to elicit simple preferences from stakeholders remotely and asynchronously, inspect the elicited preferences, and update their preferences as needed. We then obtained preliminary evidence of utility from 2 user studies. The response in both cases was largely positive, and the feedback provided useful insights.
We proceed as follows. First, we discuss the data and task abstractions we developed from real-world GDM scenarios. Next, we discuss our evaluation of visual encodings for use in preference inspection and offer preliminary guidelines for GDM support tools. We then discuss the design, implementation, and evaluation of a prototype based on those recommendations. Here we discuss the synthesis of data and task models from GDM scenarios. This section includes the characterization of the scenarios and decision makers, as well as descriptions of our data abstraction and the visualization tasks to support GDM goals. We examined 7 different GDM scenarios, from buying a gift to responding to a nuclear crisis. Note that, as shown in the table, the numbers of alternatives and evaluators vary considerably. Our elicitation methods involve in-person interviews as well as examining published sources. We identified a number of situational features from which we were able to derive 3 classes of decision makers. Specialized, dealing in one-time, very high-stakes decisions that can take days to make. Professional, dealing with medium to high-stakes decisions which may need to be made periodically. And casual, dealing with low-stakes decisions. At the level of scoring alternatives directly, we identified the following domain-independent entities and functions: a set of 1 or more alternatives, a set of 2 or more evaluators, and preference models represented by functions where an evaluator scores or ranks an alternative. In the language of visualization, the sets become dimensions and the functions in the preference models become measures. We call the measures AltScore and AltRank, which can be aggregated over the evaluators to obtain the derived measures total score and total rank. The process of obtaining visualization task abstractions for GDM begins by coalescing the goals from the GDM scenarios into a hierarchy of domain-independent goals. The first 3 goals, discover viable alternatives, discover sources of disagreement, and explain individual scores, pertain to understanding evaluator preferences. The fourth, validate model, focuses on determining whether adjustments need to be made to the alternatives. Finally, there may be other nuances of the problem that are not captured by the preference models. This will be an interesting area to examine in its own right as visualization guidelines for preference inspection become better established, and so we leave it for future work. For each of the identified subgoals, we enumerated high-level visualization tasks to support it. Here we list the tasks to support the goal of discovering viable alternatives, including those with the best score, either across evaluators or for a given evaluator, or those with low variance in scores across evaluators, indicating high agreement. We found that many of the visualization tasks consisted of the same underlying operations with different inputs, and so we identified those fundamental visualization tasks, which we call auxiliary task functions. We found that all of the high-level tasks we identified could be expressed as sequences of these functions. For example, the task to find trade-offs in the AltScores between 2 alternatives, A and B, can be accomplished by locating the AltScores for alternative A, which is auxiliary task 6, then locating the AltScores for alternative B, also task 6, and finally comparing the 2 sets of AltScores, which is task 3.
Having obtained a set of fundamental visualization tasks to support GDM preference inspection goals, we can now assess the fitness of encodings in that context. We examine idiom fitness for cases where only a single idiom is used, as well as cases where multiple idioms can be arranged into a multi-form visualization. We also discuss how the auxiliary tasks can be supported with well-known interactions. To provide a starting point for future work, we look at well-known core idioms. The bar-based idioms include stacked, multi, and tabular bar charts. The point-based idioms include strip plots and their variants, such as box plots, parallel coordinates, and radar charts. We also look at heat maps as an example of an idiom where magnitude is represented with neither length nor position. As an example, let's compare Bob's AltScores for two hotels. The best encodings, shown in Group A, place the marks on a single axis or region, rendering the comparison trivial. Effectiveness is reduced in Group B by spreading the marks to be compared across axes or regions, and it is reduced in Group C by reducing precision with compressed regions or by introducing uncertainty with unaligned axes. Heat maps are included in the least effective group since differences in saturation can be difficult to detect for non-adjacent regions. We performed this kind of analysis for all of the auxiliary tasks we identified for each possible set of inputs. The results are given in this table, where a score of 3 indicates the strongest support for the task and a 0 indicates that the idiom is ineffective for the task. It should be noted that the scores here are relative to the difficulty of the tasks themselves. While the best performing idioms overall seem to be the parallel coordinates plots, no one idiom strongly supports all tasks, and so we recommend using multiple idioms in a multiform design based on target user class. Since casual users are less likely to deal with a significant learning curve in obtaining support for their decision making, our recommendations for them exclude the parallel coordinates idioms. For both casual and advanced users, we recommend using a tabular bar chart to examine preferences for each user, paired with a stacked bar chart to make comparisons between total scores while also enabling examinations of AltScores in context. In addition, we recommend the use of box plots to provide information about the distributions of AltScores, such as variance. For advanced users, we recommend allowing users to switch between comparing evaluators in the box plots and comparing alternatives with parallel coordinates. Well-known interactions can also improve support for the auxiliary tasks. Sorting, reordering, and filtering can facilitate comparisons between entities as well as the identification of extrema. Linked highlighting can be used to help locate sets of marks for a particular alternative or evaluator, while providing details on demand can facilitate identifying an alternative or evaluator associated with a particular mark.
In this section, we briefly describe the design and implementation of a prototype based on our recommendations for advanced users. Our prototype allows evaluators to score alternatives remotely and asynchronously using simple sliders. They may also enter comments about alternatives to provide additional insights to decision makers. This interface design is mirrored in the visualization controls, allowing evaluators to update their preferences in a consistent way. Users can sort alternatives by total score or by an evaluator's AltScores by clicking on the relevant text labels. The comparison mode switch toggles between comparing evaluators using box plots and comparing alternatives using parallel coordinates. Hovering over a mark highlights all marks associated with that alternative or evaluator, depending on comparison mode, by reducing the opacity of all other marks. Basic filtering was included in our prototype by allowing users to show or hide each evaluator or alternative. Details on demand are provided in a number of ways. Hovering over a mark causes a pane to appear that identifies the mark and provides the evaluator's score and commentary. Numerical values of the marks can be displayed by toggling an overlay for the bars and with tooltips for the point marks. Full names of alternatives and evaluators are also available via tooltip. Finally, clicking on an alternative in the visualization controls displays all information about that alternative provided by the decision instance creator. As already mentioned, the prototype enables an iterative elicitation and inspection process by allowing evaluators to update their preferences and comments as needed. The implementation was performed using well-known packages comprising what is known as the mean stack. The front end was created using Angular, and the back end was created using Node.js and Express. Decision instances and evaluator preferences are stored on a MongoDB database. Here are some excerpts from our demo video showing how our prototype supports high-level visualization tasks in GDM. To find the best alternatives in aggregate, simply sort them by total score in either comparison mode. The box plots in Compare Evaluators mode encode estimates of variance. Locate the narrow boxes to find low variance alternatives. Identifying trade-offs between two alternatives can be enabled by filtering out the rest, and then comparing the scores for each evaluator in either the tabular bar chart or parallel coordinates plot. The best alternatives for a given evaluator can be found in either mode by sorting by that evaluator's scores, though this can also be seen directly from the parallel coordinates plot. The wider box plots indicate alternatives with high variance, implying disagreement among evaluators. The box plots also help identify outliers for a given alternative. The bar segments in the stacked bar chart indicate the contribution of a given evaluator's score to the corresponding total. Changes in ranking can be observed by sorting by the criterion of interest before making changes to an evaluator's preferences. While the box plots allow direct comparison of an evaluator's preferences to the rest, this can also be done in compare alternatives mode with parallel coordinates and linked highlighting. We obtained preliminary evidence of utility for our prototype by carrying out 2 user studies, which we discuss in this section. Our first user study involved Meridian, a group developing resources and infrastructure for marine environmental research. The study included 8 participants in 4 locations via video conference. The participants were tasked with ranking current projects in terms of priority for future work. The second study involved the Natural Language Processing Reading Group at the University of British Columbia Computer Science Department. Including 9 participants, this in-person study had the task of ranking papers to be presented at future meetings. For both studies, an email was sent to participants with a link to the prototype so they could submit their preferences. During a subsequent meeting, the visualization was demonstrated and the participants were given time to inspect the group preferences individually. Afterwards, the group discussed the alternatives and preferences. At the end of the meeting, the participants each completed a questionnaire including both Likert scale questions and free-form feedback. Most of the results and feedback were quite positive. Both groups were able to easily find sources of disagreement. The participants found most of the idioms and interactions effective. The most notable exceptions in both cases seem to be related to the parallel coordinates plot. It may well be that these scores are due to their relative inexperience with that idiom. In both studies, the stacked bar chart was deemed most effective, most likely due to its effectiveness in supporting comparisons between overall scores. All of the Meridian participants modified at least one of their preferences during the group discussion, as did half of the NLP participants. The results also indicate that the prototype can enable participatory discussions and increase information exchange.
We close with some conclusions and recommendations for future work. This work is the first step in addressing the lack of abstractions and design guidelines for preference visualizations in GDM scenarios. We have identified a set of domain-independent data and task abstractions for GDM scenarios where alternatives are scored directly. We have evaluated core visualization idioms in terms of underlying GDM tasks. We have created recommendations for developers that they may use as a starting point for developing GDM support tools in specific domains. We have obtained preliminary evidence of utility through the implementation of a prototype and 2 user studies. Recommended areas of future work include: examine additional GDM scenarios and perform design studies to identify tangible realities that may have been missed. Expand the data and task abstractions to include more complex preference models, such as evaluating alternatives in terms of their attributes. Develop guidelines for visualizations to support any all preference models.
We thank you for taking the time to watch our presentation.